Today, we're looking at code generalization. And what does that even mean? When you take a script and make it work for multiple scenarios, various user inputs, and apply broadly and robustly, that's what I mean by generalization. Recently, I received a couple questions on the channel about how to take my existing Sierpinski triangle algorithm, which works for a three-sided polygon, a triangle, and how would you change that code to make it work for a four-sided polygon, a square? And if we think even bigger than that, we can make our code work for any polygon that we imagine. When approaching the generalization of an algorithm, I recommend looking at these 5 steps. More advanced users can skip some of these. Beginners should start with number 1, which is developing code that works for a single case. In my scenario, I've already got the code working for a triangle, and eventually I want to use any sort of n polygon, such as a pentagon, but let's start by getting one thing working first, and you can check out my code and video on the Sierpinski triangle if you need to. Number 2, observe which variables in your code are hard-coded, meaning they're given specific values and aren't flexible or ready to be changed, and make sure they can be generalized based upon user inputs. Number 3 is then bounding those user inputs. We have to protect our algorithm and the code we have later on by getting rid of any values that are unreasonable. If someone asks for a 7-sided polygon, this is reasonable, but if someone asks for a negative 100-sided polygon, we're going to have issues. Once we've developed this new algorithm using steps 2 and 3, we're going to test it against number 1, the original working use case. And we're going to do this with the same inputs, and we better see the same output. This confirms that our new code is working as expected. Then we can begin testing all of the inputs, anything that a user might add, and this is within reason, but the reason is not within your reason. It's within anyone who might be using your code's reason. Your code needs to be able to handle a variety of inputs and not break. Let's take a look at the algorithm we're working with, and remember this is set up for just the 3-sided polygon, the triangle. The first thing we'll notice are these input parameters, which relates to tip number 3 from earlier. We have 2 options with these variables. The first is to bury them and keep them hard-coded and acknowledge that every time we run the script, these variables would be used. The other option is to make them publicly facing and allow the user to be able to change these based on their own interest. For this specific script, I really only want the user selecting if it's going to be a triangle or a square or a pentagon, and so I'm going to define a new variable here that'll be the number of vertices for the shape to have, and that's what I'll have publicly facing. I'll then bury these in the code so we don't have to worry about it. At line 10, we begin to define the vertices, the physical points in 2D space that form the edges of our polygon. Now, this is extremely poorly written because each point is defined as a separate variable. This is inflexible and not going to be useful at all. This relates to tip number 2 from earlier. We're going to need to write a vertex generating bit of code right here. So if I give you a 5-pointed object, we define those 5 points in a single data structure. Now we run into the loop. If this part is confusing to you, I recommend watching the previous video on this topic, which explains the actual algorithm. But we generate a random vertex point to go to, which is just an integer here. And then we're using this switch statement here. Now this switch statement was used purely for demonstrative purposes, but in reality, this is not going to be flexible enough to handle what we need. You can see there's 3 cases here because we were dealing with a triangle, but there's no 4th case to handle a square or a 5th case to handle a pentagon. So again, we're going to need to change this up and generalize this part of the code relating to tip number 2. Then we're just saving the variables, which should be fine, no change needed there. And we're performing the plotting operation at the very end to show what the points look like. We might have to change some things here because we're going to be getting rid of these variables in this case, but that's more of a code update rather than actually doing a generalization. And at the very end, we have the midpoint function defined, which just calculates the midpoint between 2 inputs. Do note that in this algorithm, we can actually change the weights here and here, which will affect how our fractal geometric shape is formed, and we'll get into this a little bit later in the video. Let's fix this portion of the algorithm, which will generalize these hard-coded 0, 1, 2, and 3 variables into a overall general vertex creator. We need to come up with some vertex generator that would take an initial input of the number of sides, let's say 5, and then give us the 5 points that form the pentagon, like this. But this needs to be generalized so that when we give any value as our input, we generate shapes in a repeatable manner. To do this, I went back to some basic geometry, and we can think about the XY plane as such, like this. Now, the first point is always going to be at 0 degrees. If we can recall back to trigonometry days, 0 degrees points in this direction, so every single shape will have this as its first point. And then we need to think about the next angle that'll come. So for a pentagon, will be around here for all of our points. And we need to think about what angle goes from 0 to here. What is that angle, theta? Now, it turns out there's some equations online that I looked up, and we can find the interior angle of certain shapes using this formula. 1 over n times the quantity 2n minus 4 times 90 degrees, and this keeps us in degrees rather than radians. This gives us the interior angles, and we actually want the exterior angles, which is going to be 180 minus that interior angle. Now, this video is not on mathematics, so I'm not going super into detail here, but this came from some trial and error when I was developing the algorithm. The important thing is that we now have a variable inside these equations that are controlled by our input. So now for any shape, we're going to have a flexible equation that adapts and then creates the different vertices that we actually want. And now that we have the vertices and the relative angles, we can then just use cosine and sine functions to convert these distances and angles into actual XY coordinates. We are back in MATLAB and we're going to change lines 11 to 13, but before we do so, let's save this version and create a new version that we can be experimental with. We want this version of the code to always be functional, so we have something to fall back on. I copied over the contents of the original script into a new .m file genFractal, and we'll be making our changes here. Here is the updated code. The first thing we did was add in a variable that contains the number of vertices in the polygon. And then I've also been very clear about the data type we're creating that the vertex generator will put points into. So the first coordinate for each shape will always be the same. It'll be whatever this radius is here, which is fine as 10 right now. And then the y coordinate will be 0. And that is basically the 0 degree point that will be the same for each shape. And then we'll add in x2, y2, x3, and y3, and so on. And to do this, I've written the following code. We start with the current angle being 0, and then in the for loop, we're actually going to increment by the exterior angle, as discussed earlier. This line calculates the interior angle. This line calculates that differential exterior angle that we add every time. And then we're doing the cosine and sine of those angles to actually get us our points in 3D space for the x coordinate and y coordinate of each vertex. It is always good to check that code is working before going further. So I'm going to add a section divider right here and then just run this above code to make sure it makes sense. If we run this with 3, we're going to get two outputs, 120 degrees and 240 degrees, which comes from line 21, and that confirms that we're moving around our unit circle correctly with these angles. If we go to 5 vertices, we get a few more outputs, and again, we're moving around the unit circle appropriately. This confirms that this section of the code is working well, and we can move on to fixing those switch statements. As mentioned earlier, in this for loop, the switch statement is not flexible because the cases do not change based on the number of vertices we're working with. So we're going to remove this entirely. The entire switch statement can be replaced by this one line, which simply uses the random event, which now needs to go, instead of from 1 to 3 to 1 to the number of vertices. This selects an event, and that event is used as an index into the points matrix that we created earlier. So we can simply index in there, grab the point that we're trying to go to from the current point using our calculate midpoint function. Lastly, we need to simply update our plotting function right here with the new data type we created in points, and then this code should be good to run. First thing we'll test is 3 vertices. As you can see, we get the same expected shape. Now it is rotated, but that's only because we decided that first point for repeatability purposes will be going to the right from 0, 0 here at that 0-degree incline. So for all intents and purposes, our code is running well. Now what we need to do is try different shapes. If we run this with, say, 4 vertices, we're going to get some garbage output. And this is because the algorithm is actually working fine, but it's the weights in the calculate midpoint function that need to be tuned. Here's an example where we change the weights of the current position to 0.75 and the target position to 1.25. And when we run this, now we actually see that Sierpinski action, the Sierpinski carpet we would expect. I can't really explain why these weight values create this shape. I honestly found it from more experiment, trial, and error, because if you go to different numbers of vertices as well, these weights need to change. With some experimentation, I defined a differential weight here that actually depends on the number of vertices. Again, this is not hard science, it's just something I came up with for fun. And if we add the number of vertices then to our calculate midpoint function, and make sure we include the vertices as an argument right here when we call calc midpoint, then this becomes fairly flexible for a wide range of vertex inputs. And you can see we can create beautiful geometry no matter the number of vertices. Pretty cool. The one thing we really have not done yet is protect our code in case this user input vertices becomes some wild value like -4.5. When this happens, we get an error in our code and we want to avoid this. In order to protect my code from errant user inputs, I made sure to specify which inputs should be changed by the user, here are these user inputs, and then which ones are actually going to remain hard-coded because they don't vary on the number of vertices, and these should not be changed by end users. So the vertices can change. This can go from -4.5, let's say, and I need to find a way to correct that value to make it a valid value in our code so things don't break. Hence, I added this fix user input section. The first thing I'm doing is always going to round this vertice value, so we're dealing with integers. Then I'm checking if the vertice is less than 3, in which case I'll just simply fix that vertice to be the value 3, and then send an output to the user telling them what I did. Firstly, they made an invalid input, so I'm switching the number of vertices to 3. And then in the case where the number of vertices is greater than 25, I've noticed that seems to be a good upper limit for testing this current fractal framework. Then I'm setting the value just back down to 25, and again, letting them know they inputted a very large value, in which case we're just going to drop back down to 25. So if we run this now with -4.5, we actually just run the simple triangle algorithm, and if I inputted 4.5 regularly, it should just run the 5 vertice algorithm because we're rounding those values. And if I increase that to 40.5, well then we're just going to switch back down and run the algorithm at 25. Again, defending ourselves from this code breaking due to foolish user inputs. Bringing things full circle, we first developed that initial code to work for our triangle, and things were working really well. Then we went in and we generalized those two sections. We got rid of that switch statement, and we also made our vertex generator. At the very end, we bounded those test inputs, the number of vertices, so that we protected our algorithm. If someone inputs 4.5, we correct that to be something reasonable. And then we went ahead and we tested that new code against the original, and we had that same triangular output. It was rotated, but it's the same idea in general. We'll give that a check. And then we started testing all those scenarios. What if the input was 450? What if it was negative 4.5? And we were able to correctly, based on what we did from number 2, treat those variables appropriately and ensure that the algorithm still runs. Hope you enjoyed this. Really appreciate you watching to the end. Please consider liking and subscribing to support the channel. I'm always thrilled to be providing content for you all to become better programmers. Thanks and have a great day.